Okay, so here's yep. Yep. So I just started recording it. Yep. Yeah, I'm finding that I'm forgetting recording it, so let um, when I start something, say prompt me. It's not your job, but I'll try and remember. Okay. All right. So this is an interesting problem. Tectonic plates. Do you guys know what tectonic plates are? Okay. So here's a brief summary of it, and then do you guys know the radius of the Earth? It's about 4,000 miles. Okay. 6,400 kilometers. But the reason I'm writing that is because the top 1% of the Earth, so this is 1%, which is 40 miles. Okay, that is rigid and it's sort of broken up into pieces. And because of the weight of this guy, you take a rock and you press it hard, you increase pressure on it, it becomes plastic. Okay, and if you increase more pressure, then it becomes solid again. But right now in this area, this thing is plastic. And it's called the asthenosphere. All right, so you have these plates, these large plates that are floating on this asthenosphere, the plastic layer. Okay? And what is happening is, so heat is coming up again, and these plates are in constant motion. Okay? So to get a sense for the size of the plates, so there are the large plates. Okay? So those are all the plates. Okay, and this diagram also shows you which way the plates are moving. So these two plates are moving apart and so on. These plates are moving apart. These plates are moving together and so on. Okay. So what happens is, so if these two plates are moving apart, if this plate is denser than this plate, this will subduct. Okay. And they'll get stuck, and when they slip, that's when you have earthquakes. What this also does is, okay, when plates are moving apart, that's where magma comes up, new plate is being built, but the surface area of the Earth is constant. So if you create 100 square meters of new plate, you got to destroy 100 square meters somewhere else. Okay? And so that's what's happening. All right. Now that's just that's a simplified story. Okay. The problem itself is not that complicated. What we are going to do is we're going to calculate the velocity of plates. Okay. And these plates, you saw that some of the plates are about 4,000, 5,000 miles across from here to Europe. And they move about 2 inches a year. Okay, that's the speed at which they move. Yep. All right, so tectonic plates are large segments of Earth's crust that move slowly. Suppose one such plate has an average speed of 4 centimeters per year. So see there, about 2 inches a year. What distance does it move in 1 second? All right, I will calculate both things just okay, to illustrate a point. So What is the speed? The speed is 4 centimeters per year. And you want to calculate it in seconds, and we'll convert that to meters. So for the prefix C is 10 to the minus 2 meters. And a year is, 1 year has 365 days. Each day is 24 hours. Each hour is 3,600 seconds. So I've done a whole bunch of conversion all in one shot. Okay. So this is the velocity of the plate. All right. So there's the velocity of the plate. Okay. Now the reason I did that is, well, I want to prompt you. Does that number ring any bells? I'm sorry? Oh, I mean, when I say does that number ring any bells, I'm not talking about this number. What I'm talking about is this number. Very good. So that's what I want you to think. Okay, so this is the size of an atom is 1/10 of a nanometer. So this is 10 atoms. That's 12 atoms. So this plate that is 4,000 miles across is moving at the rate of 10 atoms per second. All right, so that's what you just found. Yep.
How come you did it to two decimal places?
I'm sorry?
The two decimal places, is that
Um,
reference?
No. All right. It doesn't matter. Yeah, that's not important. Okay. All right. So, by the way, so evidence for this tectonic plate, some fellow by the name of, again, there's interesting stories behind these problems. Some fellow by the name of Wagner in 1900s, 1905. Well, what that found was, okay, so let's go back here. So what they had, this is over several years, that found fossils here and fossils here that were alike. And so this guy proposed that maybe all the continents were together at one time. This was in 1900. And of course, everybody called him crazy, because how do you move a continent, right? And so when they were, after the Second World War, when they were mapping the ocean floors, they found this mid-Atlantic ridge, and they found magmas coming up to the surface, under the ocean. And that was the first evidence for tectonic plate motion. Okay. And we'll talk about other evidences. So we might as well talk about it now. Yeah. All right. So anyway, So, well, let me get back to that. All right, so let's get back to this one. So again, he had proposed that, and how do you move the continents? Eventually, 50 years later, we found evidence for that. But what I'll do is, we'll calculate how long does this take for the two continents to go apart. Okay. So it turns out now we know a lot more. These supercontinents form in 400 million year cycles. Okay, so Africa and South America were roughly together, roughly 200 million years ago, and we'll calculate that. Okay, so we'll see that. Again, this so part B. Now, what is the speed in kilometers per million years? Okay, so we'll calculate how. So you just calculated in 1 second the plate moves 12 atoms. Now we'll calculate how far does the plate move in a million years. Okay. So V is okay. A centimeter is 10 to the minus 2 meters, and a meter is 10 to the minus 3 kilometers. Okay, so I'm doing two conversions at the same time. Let me know if you do not understand. This is a million year. A million years is 10 to the 6 years, and so I had to multiply by 10 minus 6. 10 minus 6 times 10 to the 6, that's 1. Okay? All right. You guys understanding this?
Could you explain that again?
Okay, what did you have in the denominator? A year. Okay, so you don't want to change that. I put a million years here. That is 10 to the 6 years. So I'm multiplying by 10 to the minus 6. Okay. All right. So now I'll bring this to the top. That becomes 10 to the plus 6. That's minus 5. So that's 40 kilometers per million years. Okay, so 40 kilometers is roughly from here to Palm Coast. Okay, so if we were at the edge of plate here, in a million years, we'd move to Palm Coast. That's how far, okay, a plate moves. Okay. Now, so if you wanted to calculate this, okay, so how far do you have to move this? Let's say this is about 4,000 kilometers you have to move. That's 100 million years. Okay, so there's rough ballpark answers. All right, so even though some of these problems are fairly simple, well, there are stories behind. If you have if you think a minute about it, there are interesting stories behind them. Yeah. All right, guys. Any questions on that? Yep.
So you're converting centimeters to meters and then meters to kilometers?
That's right.
Okay.
Yep.
In the centimeter
Mm.
per second question,
Mm.
or I think it was the last question,
Mhm.
we converted automatically to meters. When we're given something other than the base unit, are we expected to convert it to the base unit?
Well, no, it'll say it. It'll say it.
Okay.
No. All instructions will be explicit, and if you don't understand, what's that?
I think it was for the velocity question of those centimeters a year. We converted to meters a second.
Mhm.
So does that imply that we're converting it to meters?
I'm sorry.
Does that imply that we convert it to meters, or can we give?
Well, does it say that it's a base unit? No, it was a base unit. That's why I converted.
Okay.
Yeah. That's the language du jour. All right, so hey guys, I don't like background noise. Okay. All right, the average distance between Earth and Sun is 1.5 times 10 to the 11 meters. The Earth-Sun distance is roughly 100 million miles. Okay, 150 million kilometers. Okay, calculate the average speed of Earth in its orbit in meters per second. What's its speed in miles per hour? Actually, I'm going to calculate it in kilometers per second. Okay, because that's a good number to remember. Okay, so here's what we're going to do. What we're going to calculate is the speed of the Earth around the Sun. Okay, and in kilometers per second. Anybody have any idea of how fast the Earth is going around the Sun? Okay, so anyway, you want to remember this, so we'll calculate this. Okay. I'm sorry?
Is it 17,000 miles an hour?
That's the speed of the space shuttle.
No.
Okay. It's actually 4 times faster than that.
No.
All right. The speed is the distance traveled divided by the time. Okay, so the distance traveled divided by the time. The distance traveled is 2 pi r, and time is 1 year. That's the time it takes Earth to go around the Sun. Okay, so 2 pi into 1.5 into 10 to the 11, and I'll convert that to kilometers right there. 11 into 10 minus 3 kilometers. Okay. Let me know if you do not understand it. So what have I done? This was in meters, and a meter is 10 to the minus 3 kilometers. Okay. Divided by 1 year. 1 year is 365 days, 24 hours. Okay. Yep.
For some reason the projector screen is behind. I think what you're doing. You're not writing anything right now. But right now it looks like you're writing stuff. I don't know why the projector screen is slightly.
Well, I guess the internet is supposed to work at the speed of light. Maybe the light speed slowed down. All right. You guys understanding this conversion stuff? So for instance, 1 year I was lazy. 1 year is this, the denominator is converted like this. But again, I'm not going to be doing this all the time. Days, 1 day is 24 hours, and 1 hour is 3,600 seconds. Okay, so this got converted to that. That's how I got that. Okay. All right, so and again, here's another trick that you want to learn. Okay, when you're typing on your calculator and stuff like that, what you want to do is to minimize mistakes. You want to take care of powers of 10 in your head. That's easy to do. Okay, so this is, we'll say this is 3.65 times 10 to the power 2. Another one there, 3 plus 3, 6. In the denominator, you have 10 to the power 6. In the numerator, you have 11 minus 3 is 8. 8 minus 6 is 2. Did you guys understand that? All right. So that's what you want to do. And now the rest is 2.5 into 1.5 divided by 3.65 into 2.4 into 3.6. Okay. So you're less likely to make mistakes that way. Anyway, that's my habit, and I like that, and I'm going to stick by it. So I'm just sharing tricks of the trade with you guys. Okay, so that's a good number to remember. The Earth is traveling at 30 kilometers a second around the Earth. A low Earth orbit object travels about 8 kilometers a second. So if you're flying about 250 miles above the surface of the Earth, that's your speed. The International Space Station is going at about 8 kilometers a second. Any questions on that? Okay. So this thing says, consider the physical quantities S. S stands for is distance, velocity, acceleration, and time, with dimensions S. This quantity has dimensions of length. Velocity has dimensions of length over time. Okay. So when you write a square bracket around a variable, you're asking for its dimensions. Okay? Acceleration has dimensions of length over time square. Okay? And so on. All right, so they ask, are these equations dimensionally consistent? What does that mean? Is the dimension on the left-hand side the same as the dimension on the right-hand side? Do you have apples on the left-hand side and apples on the right-hand side? Okay? So that's a quick check to see if the equation is potentially right. Okay? Because if you have apples on the left-hand side and oranges on the right-hand side, even I can tell you that's not a correct equation, right? Okay, so that's the first check we'll do. We'll do dimensional analysis. Okay. So for instance, I'll just do one. Okay, I'll do part B. Okay, so S equal to BT squared plus 0.5 AT squared. All right. So what we want to do is, what we are trying to verify is that is the dimension of the left-hand side equal to the dimension of the right-hand side. So each term here, the right-hand side is the sum of many terms, of two terms here, and each term has to have the same dimensions. Okay? All right. The dimension of S is L. Is that equal to dimension of VT squared? Dimension of V is L over T, and this is T squared. Okay? So right away you can see that the dimension of the first term is L times T, which is not equal to that. This guy doesn't have that dimension. So we already know that this equation can't be right. Okay? And just, and the dimension of 0.58 T squared is L over T squared. The dimension of A is L over T squared, and the dimension of T squared is T squared. So the second term has the right dimension. The first term doesn't have the right dimension. Okay? So without knowing any physics, you can tell that this equation is incorrect. Okay? So all by asking the simple question, if you have apples on the left-hand side, you need apples on the right-hand side, you can eliminate the infinite countably infinite number of wrong equations. Okay. Did you guys understand that? Any questions? Go ahead. I'm sorry?
It's low.
How slow is it?
It's really slow.
It's going around the world 3 times. No way. So I'm talking and there's nothing on the thing. Should I reboot?
I think it's just the internet.
It's probably just your, it's your stream, it's your upload. It's probably just running slow. It should be okay. It should be fine.
It just takes a while.
What?
It just takes a while.
It starts off fast and
Yeah,
then
it-
especially gets slower.
Yeah, it'll start off fast and then it'll get slow.
Well, are you guys understanding it? I mean, I'm talking. Okay, not it. All right, so let me do one more problem. So this is a Fermi calculation. Okay. So assume the human body is primarily made of water, and that is roughly true. We are just a bag of salt water. Estimate the number of molecules in it. Note that water has a molecular mass of 18 grams per mole, and there are roughly 10 to the power of 24 atoms in a mole. Okay, so number of water molecules. Okay. So again, this is a Fermi calculation, so you have to start off with assumptions. So an average human being, I mean, our mass is about 50 to 70 kgs, but I'm not good at math, so we'll do 100 kg for the size of an average human. Okay. And the molecular mass of, again, this is just ballpark numbers we're doing. It's 18 grams per mole. So we want to find how many moles are there in a human body. Okay. So that is, we'll divide that 20 grams per mole. So we'll make water a little heavier. Why did we do that? 100 divided by 20 is 5, which is easy to do. Okay. So we're doing calculations in our head. Okay. And so what you get is the mass will cancel. You'll get moles on the top. And then what do you have to do? You have to multiply by 10 to the 24 per mole. So now you have a number. And this is something you can do in your head. Okay? Now, so this is, okay. This is 100 kg, which was 10 to the 3 grams, 20 grams. So the gram cancels and the mole cancels into 10 to the 24. Okay? So what did we get? This is 5 times 10 to the 27. So, in your body, you have about 5,000 trillion water molecules. Very cool. All of 30 seconds. Yeah.
Are there any keywords
estimate.
Estimate is the keyword.
Mhm. Yep.
So with the Fermi calculations, it's not, like, there isn't exactly a correct answer, it's
Right.
just if you show logical thinking thing.
Right, right. Well, how do we know if this Fermi calculation, if you come up with an answer of 10 5 to the power of 1021, you did something wrong. Okay. Yeah. All right, guys, so we'll stop here.